Well, hello there. Today is whatever today is. Once again, I'm not sure what day you're viewing this. Um, this topic is Unit 2, Topic 2, Energy. We're going to be going into far more detail on this stuff later in the year, but for now, we're just going to take a look at the fundamentals. What is energy? What are the types of energy? And how can you convert energy from one form to another? Energy, by definition, is the ability to do work. So, for example, mowing the lawn. That's work. Sometimes you're on a riding mower. Sometimes you got a push mower. I have a friend who has one that actually has rotating blades that with no engine at all. But that's work. Work is defined as using a force to move an object a distance. If the object is not moving, then work is not currently being done on it. So a baseball that's thrown through the air, work has been done on that baseball. But if all you're doing is holding it in your hand, work is not being done on that baseball at that moment. So we have two kinds of energy: energy where work is being done right now, or energy that could be put to use to do work. We call energy that's being used right now to do work as kinetic energy. This is energy of motion because work is making an object move a distance. Whee! Anything in motion has kinetic energy, anything at all, as long as it moves. And this includes every atom in your body. Even in solids, atoms and molecules move. Even if they're just vibrating back and forth in place, they're still moving. I mean, think about it. When you're in school and you're sitting at your desk and everyone else is sitting at their desk, they're not moving relative to each other, but you're still fidgeting in your desk. Maybe you're scratching an itch, maybe you're drawing a doodle, maybe you're checking a TikTok or whatever it is. You're still moving. You're just not moving relative to each other. So anything that is in motion, even atoms in a solid, have kinetic energy. The hotter it is, the more kinetic energy there is. So temperature is a measurement of the amount of kinetic energy you have. So cool gas, that gas is cool, man, has fewer and less energetic collisions because the molecules have less kinetic energy, as opposed to hot gas. More and more energetic collisions caused by the fact that these molecules have a greater amount of kinetic energy. If we were to put a thermometer in, the cool gas would have a lower temperature, the hot gas would have a higher temperature. Speaking of temperature, this is how we measure kinetic energy. Big things we can measure pretty easily. I mean, radar can be used to measure how fast you're going down the road or how fast a fastball is going from the pitcher to the catcher. But when you're dealing with really tiny things that you can't see, we take their average speed by measuring the temperature. Now, understand that if you've got a glass of water, not all the molecules are moving the same speed. But if you take the average of all their speeds, that would be the temperature, the average kinetic energy of a system. So you just stick the thermometer in, and the molecules, if they're warmer than the bulb, will hit the bulb, causing the bulb molecules to move faster, causing them to expand through the glass tube. And we can measure that expansion very easily. As kinetic energy increases, this is measured as a higher temperature. And as kinetic energy decreases, it's measured as a lower temperature. Up and down. Okay. Let's introduce you to some of the characters in the temperature game. First, we have Daniel Fahrenheit, who recorded temperature. This is Daniel Fahrenheit right here. What he did was he measured salty ice water because water freezes at a certain temperature, but salty ice water takes a lot lower temperature to freeze. So if you make a saturated solution of salty ice water and put a thermometer into it, Fahrenheit marked this off as being 0 degrees Fahrenheit. Now, water, pure water, will normally melt or freeze at 32 degrees Fahrenheit. So this is significantly colder than that. Then he's looking around for something warm to get a 100-degree point, and he uses an armpit. And the temperature he gets is 100 degrees. As you know, body temperature on average is 98.6. So maybe they were running a slight temperature that day. Huh. So, salty ice water and armpits may not be the best way to measure temperature for a consistent scale, so along comes Anders Celsius. And Celsius's scale chooses two fixed points that are easily reproducible: the freezing point of pure water, which he marked off as being 0 degrees centigrade, and boiling pure water, which he marked as 100 degrees centigrade. Now, centigrade literally means scale of 100. So if you divide it into 100 equal parts, each degree would be 1 degree centigrade. This scale was later named for Celsius because it also starts with a C, which is why we don't call it centigrade anymore. When I was a kid going to school, we called it centigrade. But since I started teaching, we call it Celsius. So there you go. Then along comes William Thompson, who says, well, I kind of like what you did here, Celsius, but it is possible to have temperatures colder than 0 degrees Celsius. You can get colder than freezing. Any good winter's day is going to get you lower than freezing. And all other scales start at 0, because if you have no mass, it's 0 grams. If you have no volume, it's 0 liters. So Kelvin set out to make a scale of temperature that starts at 0, and he used Celsius's scale as his standard. What he did was say, well, I kind of like the fact that you have water as your standard because we can find it anywhere. However, through experimentation, we found out that all molecular motion stops at negative 273 degrees Celsius. That is the coldest temperature it's possible to have because that is the point at which all molecular motion stops. And you can't have less than no molecular motion. So Kelvin found his starting point for his temperature scale and called this 0 Kelvin. Not degrees, but Kelvin, like grams or liters or meters, just a unit of kinetic energy. Then, the freezing point of water is 0 degrees Celsius, which is 273 degrees above absolute zero. So we call this 273 Kelvin. He kept the size of the degree the same, he just reset the starting point. The boiling point of water is 100 degrees Celsius, which is 100 degrees above the freezing point. So this would become 373 Kelvin. So the Kelvin temperature will always be 273 above the Celsius temperature. So if you want to convert Celsius to Kelvin, you add 273, and Kelvin to Celsius will be subtracting 273. So if we want to convert Celsius to Kelvin, we add 273. Kelvin to Celsius, we subtract 273. That's kinetic energy, energy in motion, energy that is being used to do work right now. But is there a kind of energy that's not doing work right now that could be put to use? Well, sure. We call that potential energy, stored energy. It's not doing work right now, but it has the potential to do work. It's like money in the bank. We're not using it to buy stuff now, but it certainly has the potential to buy stuff later on. Examples would include being on a swing set. You have maximum potential energy when you're highest in the swing, and the lowest potential energy when you're lowest in the swing. This is due to gravity. Most of these are due to gravity. In a bow, when you pull back on the string, you deform the limbs of the bow. This acts as a spring, and when you let go of the spring, the wood snaps back to its original position, pulling the string forward, which also pushes the arrow in the direction you've aimed it. When you go on a roller coaster, all the energy you need for that ride is given to you in the first part of the roller coaster when they take you up that long hill. You get to the top, and then you look over and you realize you're in for the ride of your life and you go over the top. Every bit of energy you use for the rest of the ride was stored up in that first climb up that first hill in the roller coaster. Of course, bungee jumping requires gravity. Gasoline has chemical energy. So does dynamite. A coiled spring stores mechanical energy, just like a bow. And of course, chemical energy is what allows you to get calories from your food. So all of these are examples of energy that's not doing work right now, but certainly could if you gave it a chance. We measure potential energy indirectly. You can't measure something stored directly. You have to convert it first. So what you can measure is how much potential energy was there before I released it. So what you do is you break the piggy bank and you measure how much money there is in there. So we use a device called a calorimeter. I'll show you how that works. And the unit of measurement for potential energy is joules. Not that kind of joules. Chemical changes result in thousands of joules being absorbed or released, kilojoules, whereas nuclear changes result in millions or billions of joules of energy being released. The energy is stored before the change, but is released during the change. Heat will always flow from where it's hot to where it's cold, because it's kind of like nobody ever said, okay, turn on the dark when they wanted you to turn the lights off. Dark is merely the absence of light. Cold is merely the absence of heat. And heat will naturally flow from where it's hot to where it's cold. So if you're standing in a nice hot room on a cold winter morning and you open the door and your mom yells at you, there's two things that your mom can yell at you. Close that door. What are you trying to do? Let all the cold air in? Close that door. What are you trying to do? Heat the whole neighborhood? Only one of them is thermodynamically correct. So if your mom says, close that door, what are you trying to do? Let all the cold air in? Say, no, mother, that is thermodynamically incorrect. I'm trying to heat the whole neighborhood. See how that goes for you. The temperature will eventually equalize. Now, the law of conservation of energy is just like the law of conservation of mass. You cannot create or destroy it. You can only convert it from one form to another. So, for example, we can convert potential energy to kinetic or kinetic to potential, and each type of change has its own unique name. So, for example, the energy stored in ice cream can be eaten and give you enough energy to run, and that is a direct conversion of energy. The total amount of energy remains constant over time. We don't have an energy shortage, we have a potential energy shortage. When your sources of potential energy begin running out, then you're going to be in a little bit of trouble. Sunlight is absorbed by plants, is converted into energy in the form of sugars, which are eaten by cows. And then we eat the cows, and that allows us to move. And that's not where the energy transfer stops. For example, as you're running, your body moving through the air jostles about air molecules, making them move faster. And when your feet hit the ground, that energy is transferred to the ground, and you hear that energy in the form of sound waves. So the energy is constantly in motion. It may just go from a more usable form for us to a less usable form for us. And of course, that energy is also converted from your ear into energy in your brain that allows you to actually realize that, hey, I just heard something. So we have potential to kinetic or kinetic to potential. So what are these called? Well, if you take energy that's stored and release it, like in an explosion, This would be an exothermic change where energy exits its stored state. The energy is released, like open the cage and let the tiger loose. Ooh. So if we burn something, we're taking energy that's stored in the chemical bonds, that's potential energy stored in the chemical bonds, and we release it as kinetic energy. Potential decreases, kinetic increases, and we feel that kinetic energy as heat. That's exothermic changes. The potential energy lost will always equal the kinetic energy gained. That's the law of conservation of energy. The other way, kinetic to potential, where we take energy that's moving and then we store it, we kind of like cram it into a suitcase, is called endothermic. We're putting energy endo, a stored state. So, in the case of a chemical cold pack, what's happening is kinetic energy from the surrounding environment is absorbed by the reaction and converted to potential. And this will cause the molecules in the surroundings to move slower. So, we have kinetic energy in the surroundings, but that kinetic energy is absorbed into the reaction, which means there's less kinetic energy. Less kinetic energy means less temperature. It feels colder. So exothermic changes cause the surroundings to heat up, where endothermic changes cause the surroundings to get cooler. And again, the kinetic energy lost must equal the potential energy gained. Now, changes that release potential energy and convert into kinetic energy are called what? Exothermic. Changes that absorb potential energy and convert it into kinetic energy are called endothermic. How do you measure kinetic energy? With a thermometer. So during exothermic changes, temperature goes, well, in an exothermic change, you make more kinetic energy. Since temperature measures kinetic energy, temperature goes up because there's more of what it's measuring. And during endothermic changes, the temperature goes down. You're going to be going into far more detail on exo and endo as we go on through the year. We're going to look at it in terms of energy of phase change, and we're going to take a look at it in terms of chemical reactions as well. And that is all there is to this brief introduction to energy. It's been fun. Bye.